Continuing with the story of implicit differentiation, we got to a point where, with this function, we now have this formula, dy dx is a minus the ratio of two partials. Not a way we could have phrased it in BC calculus, but let's see what the answer is. Let's see, for this example, if big F of xy is x squared plus y squared minus 1, then big Fx is 2x, big Fy is 2y, and I get that dy dx is minus 2x over 2y minus x over y. It's the same answer that we got in this way. And those 2x and those 2y, those are exactly those partials showing up. This isn't really a new way to do it. It's just saying that this stuff you always get, the stuff that doesn't attach to a dy dx, is always the partial with respect to x of whatever function you started with. And the stuff that's attached to dy dx is always the partial with respect to y. So in BC, sometimes you get rather messy versions of this, but you notice that there's some stuff that has dy dx's in it and some stuff that doesn't, and you separate those out, and you move this over with subtraction, you move this over with division. Well, we're just really formalizing that and giving a name, essentially, to the stuff that doesn't involve dy dx. And guess what? It's exactly the partial of this function of two variables with respect to x. And the stuff that does involve dy dx, it's exactly always the stuff, it's always the partial derivative of this with respect to y. Okay, so here's, phrasing this in terms of multivariable, the main thing I want to emphasize again is it's pretty tricky, and it really rests on this distinction between a partial derivative with respect to x, which would be going this direction, and a total derivative, which means stay along the level set. Now, what happens if we make things a little more complicated? Let's look at an example. Let's suppose we have, get an example out of the book here. Suppose we have yz equals ln of x plus z. That's one equation in three variables. What is that going to produce geometrically? It's going to produce some sort of surface. Just like one linear equation in three variables produces a plane, one general equation in three variables should produce some sort of curvy surface. And we're going to have various things to say about those surfaces, but here's one way to talk about them in terms of implicit differentiation. In principle, I could solve for one of these variables in terms of the other. And in fact, in this one, I picked one. I probably shouldn't have picked one, where I can actually solve for z in terms of x and... Oh, no, I can't. Just kidding. I can't solve for z in terms of x and y. I was misreading it. If I try to do that, the z doesn't come out here. Okay, I could actually solve for y, that's what I meant, in terms of x and z. But if I want to solve for z in terms of x and y, it's not going to happen. I can't take the z out of the ln. Okay, so that's not going to be useful. But in principle, we would hope that it is some sort of surface, and that for every x and y, there is actually some one solution, even if I can't get it in some simple form using algebra. So let's see if I can use the same ideas to figure out, for example, what is the partial derivative of z with respect to x at some particular point. So suppose I've found a point on the surface, which in itself might be hard, because that equation is hard to solve. But suppose I have some points that's on that surface, and I want to figure out how steeply does it go up or down if I go out in the x direction. That's partial z, partial x. Is it sloping down and towards me or up and towards me? And I want to be able to figure that out. Well, here's the deal. I just create a function of three variables now. I put everything on one side. And I go ahead and take the partial derivative of that with respect to x. But there's a very tricky point here, okay? As soon as we start talking about this, we have to be really, really careful about what we really mean by partial derivatives, okay? What I mean here is I'm going to go ahead and consider this surface defined by assuming this equation is true, and therefore hopefully implicitly defining z as a function of x and y. And so from that point of view, z is totally treated differently from x and y all of a sudden. It's considered to be the dependent variable defined by x and y. So one way I could emphasize that is I could say, take the partial derivative of z with respect to x, setting y constant, but only setting y constant. Varying x, setting y constant, and saying z is not on the same footing as x and y at all. It's an output variable. Okay, so that's what I really want. But then, when I'm looking at big F and big F alone on its own terms, that's a function of three variables that should be on the same footing. That's something that gives me a value to every point in three-dimensional space. And so the partial derivatives that apply to big F on its own terms are rather different. Okay, so I'm going to take the partial of this equation, but I have to be even more careful. It's the analog of the distinction between the total derivative with respect to x and the partial derivative with respect to x, but it's an even more subtle version of that. And so I want to draw the tree diagram. So let's say W is big F of x, y, z, and I've got, let me write it over here. W depends on x, y, and z directly through big F. And then I want to think of this, though, as a function of only x and y. I want to think of z as being defined by x and y. And let's give a name for that. Let's say that's little f again. Okay. I want to think that this implicitly defines z equals little f of x and y. And I want to get little f sub x here. Okay, so that's another notation. This is little f sub x. Okay, so here's the tree diagram. X depends on x and y in a very simple way. It's equal to x, and so it has no derivative with respect to y. Y depends on x and y in a very simple way as well. It's equal to y. It has zero derivative with respect to x. So the derivative that I'm going to take right now is the derivative of w with respect to x. I want to take the whole chain. I want to get the chain rule involved in here. So with just y fixed. And so that's how w depends on x. If I let x vary, I fix y, but I definitely don't fix z. I let z be little f of x and y. And if you look at the treatment in the book, it's pretty good, but it does not make this distinction very clear. So that's going to be how w depends on x with both y and z held constant. Or at the same time, I'm going to write it with the f sub notation. That's just big F sub x. That's only looking at the top level of the tree. Times how x depends on x. Well, that's going to be 1. Plus how w depends on y with x and z held constant, times the partial of y with respect to x. Now that's interesting. Okay, so partial y with respect to x. Well, let me actually decorate these guys. This is with a y held constant, and this is with a y held constant. Because these two guys, the second term in each product, the second factor in each product, is about this level, about how x, y, and z depend on just x and y. The z is not one of the independent variables in this case and this case. That's just going to be 1. This guy is going to be 0. Because if I'm definitely holding y constant, and I'm asking how much y varies, it's going to be 0. Plus dw dz with x and y held constant times, and here's the key, dz dx with y held constant. That's actually what I'm interested in. That was my original question. Okay, so quickly I'm going to write it down in this other notation, and then I'll finish up in another different video. This is fx times 1 plus 0 plus fz times what I want, dz dx y. And again, this is supposed to be 0 if I'm staying on this surface. If I vary x and I don't vary y, but I also simultaneously vary z in such a way as to stay on that surface, that derivative should be 0. Finish it up next video.